Hey guys, finally I'm glad to introduce my lecture series on the similarity transformation. And similarity transformation is a very useful technique in modern control theory, and it includes eigenvalue decomposition, which works when the matrix is a square matrix, and Jordan canonic form, when the matrix is a square but has repeated eigenvalues, and also singular value decomposition. It works in general even when matrix is not a square matrix. Before we goes into those advanced topic, today I want to set some basics. This basic concept is very useful and crucial in learning the more advanced theory, and it is to understand the geometric insights of a matrix vector product. So a lot of times we will deal with matrix timed with a vector, and to compute it is actually very easy. Mathematically, let's open MATLAB, and basically we can have a matrix A. I already imported it, but there are several ways to actually import this matrix in MATLAB. The normal way to import it is import by the row of the matrix. So we can say that the first row of A is actually this, and the second row is 2.28, 0.96. So basically we input by first row and then second row here. But usually what I will do is that I will I will import the matrix by its column, because later on you will see that column vector are more kind of more frequently used when we talk about a matrix product, or talk about this similarity transformation. So what I will do is I will import the first column of matrix A, and then the second column of matrix A, and then transpose it, and you will get the same result. We can verify that our A is still the same thing. And so to compute the matrix product, you just times A with X, and in this case we can specify X is equals to 1 and 2, and then we transpose it to make it a column vector, and A times X will give you 4.4, 4.2. So that's not too important. We need to actually understand the geometric insights behind it. So the first column vector of that matrix and the second column vector of that matrix actually is two principal axes. So we all learned about the courtesy coordinates. I might pronounce the English wrong, but basically it's the x axis and the y axis. That's how we define those locations usually. For example, this point, it is 0.96 and 2.28. We're talking about x-axis and y-axis. We're giving it some coordinates. X coordinates is 0.96, 2.28. Similarly, these two defines two axes, axis 1, axis 2. It's a direction, and then this vector elements tells you that the coordinates in that corresponding axis. So coordinate 1 is 1, then we basically align with axis 1 here, and in x2, it is 2, which means that in this axis 2, this is the unit vector. then we need to times it by 2 to get to this location. And the final result, 4.4 and 4.2, is actually a vector sum of these two. So the concept that I want everyone to keep in mind is that every column vector of that matrix can be viewed as a principal axis, and then or maybe you can view it as a unit vector. It's not really unit because the length is not 1, but it is in terms of itself, it is unit. And then this corresponding elements in that vector tells you how far you want to go in the direction pointed by that axis. And then you use that elements times that vector to form a new vector and sum with the other vector. So this is in 2x2 case just for demonstration purpose. And in real life, when you deal with higher order matrix like 3x3, 4x4, it's the same. Instead of lying into a plane, we basically goes to a 3D space, or even some higher order space that a human cannot easily understand, but can not easily visualize. But the principle are the same. Whenever we encounter matrix vector product, we need to think about what is its axis, and what these elements of the vector actually tells us. And this is very important, and it will be used again and again when we talk about a later topic like similarity transformation and also singular value decomposition. Stay tuned for this advanced topic. Thank you.